Thevenin and Norton circuits are useful for many things. The one we've been talking about throughout the large majority of this video series has been simplifying your analysis. But it can do more than that. Today we're going to talk about maximum power. Imagine that I have a complex circuit that I'm going to represent as some amorphous thing that happens to have two terminals. I would like to connect a load resistor to it. Very often, I want my load to absorb the maximum power it possibly can. For example, if my load were the motor of an electric car, then it would make sense for that motor to have all the power that it can have delivered from the driving circuit. If the load isn't absorbing maximum power, then the circuit is absorbing more power than it should. The issue is, how do I know what my load should be in order to maximize the power? I'm not going to go through the derivation here. There is a derivation. It is available in many textbooks. Right now what we'll be talking about is just the maximum power theorem, and here it is. Theorem, THM. Maximum power is transferred to a load when RL equals R Thevenin. This is an extremely important theorem. We could ask ourselves questions like, what should my load be in order to get maximum power? We could also ask ourselves questions like, how can I modify my original circuit so that a 10 ohm load gets maximum power? Finally, we could say, my load can only take so much power. Will it absorb too much? Let's do an example dealing with maximum power. We're going to be looking at something called a real model of a battery. So far in this course, we've assumed everything is ideal. Your voltage sources are perfect sources of voltage. Your current sources are perfect sources of current. In reality, that isn't true. A real battery is actually defined as a voltage source, and let's for concreteness say it's a 9-volt battery, and a resistance, and typically that internal resistance is what it's called, is quite low. It's about 2 ohms to 20 ohms, somewhere around there. And I'll be honest with you, this this resistor actually comes from a real battery manual. So this 2 ohm resistance is something you might expect to see of a real 9-volt battery. So that's what a battery looks like as a circuit element. Now, a motor is an electrical device, and a motor can be represented with the circuit element M, but also as a resistance, because motors essentially are resistors once they get up and running. So, assume I want to buy a motor so that maximum power is transferred. Well, by the maximum power transfer theorem, I need a 2 ohm motor. I didn't need to do any calculus, I didn't need to do anything. I know what the maximum power transfer theorem is, and hey, look at that. I have a voltage source and a resistance. I essentially have a Thevenin equivalent. So, I can say, well, since I'm connecting my motor to a Thevenin equivalent, there we go, I need a 2 ohm motor. But let's do a little bit better than that. What if I don't have a 2 ohm motor? Say instead I have a 4 ohm motor. As a percentage, how much of the efficiency am I losing? In other words, if I could be absorbing 100% of maximum power, if it were the correct motor, what's the difference between the actual power absorbed and the maximum? If my motor is 4 ohms, let's see what happens. Here's my battery. It has 2 ohm internal resistance. and I can replace this with a 4 ohm motor. At this point, I know that what I'm doing is just analyzing a circuit. Although it's handy to talk about Thevenin, in this case I'm really just analyzing a circuit. So the first question is, well, how much power is my motor absorbing in this case? Well, there is my current, I, and I is equal to 9 volts over 6 ohms because it's in series, which is 1.5 amps. I know that my power in my resistor is I squared R, and so what I end up with is 2.25 times 4, otherwise known as 9 watts. Now, what is the maximum power that I could be transferring? Well, that would occur when my resistor is a 2 ohm resistor. The current in that case is 9 over 4, otherwise known as 2.25 watts. And so the power, which is I squared R, is now going to be 2.25 squared multiplied by R, 2 ohms, or 12.5 watts. Notice the significant difference just by changing the resistance of my motor. Now sometimes you really can't get around that. For example, you may only be able to buy 4 ohm motors. It's common to be able to purchase only certain resistance values of common components, motors being one of them, speakers being another. What you could do is modify the original circuit so that its resistance is more in line with your load's resistance. On the other hand, you might just be interested in knowing how much power you're absorbing and comparing that to your maximum power. So that's the idea behind the maximum power transfer theorem. When RL equals R Thevenin, you have maximum power, and we can use that to answer some interesting questions regarding how maximum power, or power in general, is developed throughout your circuit.